You need electricity to use pressing iron in the house, to use boiling rig to boil your water, to have light. Light is just one part of the electricity. You understand? Yes, welcome. Today we are going to be looking at current electricity. We are going to be looking at what? Current electricity. In the house, whenever the light goes up, you say NEPA has gone, isn't it? Can you do something like ironing? Can you use a boiling ring to boil water? No. Once there is no light, you cannot do any of those things. You understand? But in the proper language, you should have said there is no electricity. There is no what? Not light, actually. You understand? Whenever they take the light, say, hey, NEPA has taken the light. You understand? But what is actually doing the work is what? Electricity is what? Electricity. You need electricity to use pressing iron in the house, to use boiling rig to boil your water, to have light. Light is just one part of the electricity. You understand? Lighting is just what? One part of the function of the electricity that gets to us. And in Nigeria here, the NEPA people, they are the people supplying the electricity, isn't it? The power holding. So what is this electricity? What is this electric current that we have? Electricity is simply the flow of current. Is simply the what? Flow of current. Or you say electric current is simply the flow of charges. The flow of what? Charges. So whenever charges flow, you understand, and gets to your bulb will do what? Light. It will do what? Light. It is the flow of what? Charges. But for charge to flow, there must be something supplying the charges, isn't it? So in this our electric circuit, you can tell me what is supplying the charge? The cell. The cell. We call it battery. You understand? When you connect your battery with your torchlight, what will happen? The torchlight will on. Because there are some charges that are being supplied from the battery to the what? Torchlight. Is that clear? So this is what is functioning as the supply. Who can tell me the supply of the charge that is flowing that supplies our own electricity? Do you know about Kainji Dam? Have you heard about Kainji Dam? What of Shiroro Dam? You understand? There are many things that can supply the charges. A battery or a cell can supply the charge. You understand? Generator can supply the charge, like the one I'm having there. Like this current, what is supplying it? The generator. Then NEPAs get their own from where? The Kainji Dam, from the dams. You understand? There are also some gas plants that supply electricity. You understand? So when there is a source of charge, and this charge is flowing, the flowing of this charge is known as what? It's known as what? Current. Is that clear? So whenever the charge is flowing from one point to the other, it is known as what? Current. And that's why we say electric current is the flow of what? Electric what? Charges. Is that clear? It's very clear, huh? Now we say that it is the what? Quantity of electric charge flowing past a given point of a conductor. This is a conductor or circuit. This is circuit. You understand? A second. And that's why we represent it as what? Quantity of charge all over what? Time. Is that clear? Current I is represented as what? Quantity of charge Q all over what? Time. Is that clear? Now you can illustrate the flow of current using the flow of what? Water. Using the flow of what? Water flows from a point of higher potential. Can you see the level of water here? Is it higher than this one? It's higher, huh? This one is high potential and this one is what? Lower potential. So if you have a big bowl like this and you connect an outlet here, what will happen? The water will do what? Flow. The water will do what? And that is when you open the what? When you open the what? Good. In that same way, this cell will supply the what? Charge that will flow. When you do what? Close the what? Switch. If you close this switch, you've connected the circuit, so charge can do what? Flow. And when it's flowing, immediately it passes here. What will it do here? It will light up this place and it will continue to go until it gets to here. Is that clear? So that's the same way this one works. For current to flow, there must what we call potential difference. There must what we call what? Potential difference that is measured in volts. That is measured in what? That's what we are going to learn. You understand? So it's because of the potential difference between here and here that will allow the current to do what? Flow. The charges will flow. And the flow of these charges is known as what? It's known as what? The same way. Yeah, you understand? This place is at higher potential. This place is at what? Lower potential. So the water will flow in this direction. You understand? So when you open the tap, as if you're closing the switch, the water will do what? Flow. And when the water flow, if this thing is a thin bowl, what will happen? The water will do what? Splash. Just the same way that if you close this, the current will go what? Light up the bulb. Is that clear? So whenever there is current flow, the current can do work in the process of this flow line. It can do what? Work in the process of this what? Flow line. Just like if current is flowing from here, when it gets here, it will do the work. What work will it do here? Light up the bulb. And that's the work you also use in what? Pressing your iron. That's the work you also use in what? Using boiling ring in the house. That's the work you always do use in what? Watching television. Doing what? Listening to news in your radio. Is it not? So, when current flows, it does what? Work. It does what? Do we understand it? Can we understand why this current is doing work? Do we understand that there has to be a source that will supply the charge, that will move? And when this charge is moving, we say there is what? Current. Is that clear? This current is measured using an instrument known as what? Ammeter. Known as what? Ammeter. Current is measured using an instrument known as what? Ammeter. And the unit of measurement of current is what? Coulomb. The unit of measurement of current is what? Coulomb. And current is measured using an instrument known as what? Ammeter. And the unit of current is what? Coulomb. JAMB is going to ask you, which of the following is not an instrument used in measuring current? Is that clear? And they are going to give you what? Ammeter. They are going to give you what? Ammeter 1. They are going to give you galvanometer. Is that clear? They are also going to give you micro what? They are going to give you microammeter. They are going to give you what? Microammeter. And they are going to give you what? Milli what? Ammeter. And they are going to give you a thermometer. What will be the answer? Which of the following is not? Is not. You understand? You can use this to measure. This is the measuring instrument that you use in measuring current. You can also use this to measure very small current. You can use galvanometer for it. You understand? No, you can also use this one for smaller currents. Is that clear? But what do you use thermometer in measuring? Temperature. So the answer should be what? Thermometer, because thermometer is not an instrument for measuring what? Current. Is that clear? So in subsequent classes, we are going to learn about EMF, volts, and other things. Yes, welcome. Today we are going to be learning about electric circuit. We are going to be learning about what? Electric circuit. Electric circuit is simply the connection of electrical components using a wire. You understand? So that it can enable the flow of what? Current. It can enable the flow of what? Current or charges. So this is an example of electric circuit. Can you see it? What are the electrical components in this circuit? Bulb, switch, bar. There could be resistor. This is a cell. You understand? So whenever you connect this component using a what? Wire. Using a what? Wire. You call it what? Electric what? Circuit. Whenever you connect electrical components using wire, you call it what? Electric circuit. So we have an electric circuit is formed when one or more electrical components are connected across the terminals of a what? Cell. Across the terminals of a what? Cell. Can you see the cell? These are the two terminals, positive and what? Negative. You connect all these electrical appliances using a wire. You call it what? Electric what? Circuit. Such that the electrical energy generated by the cell, is that clear? I told you that the charges are generated by the what? Cell. So if JAMB asks you, which of the following is not a source of charges for electricity? They will give you cell, they will give you generator, they will give you accumulator, they will give you battery, they will give you telephone. What will be the answer? Telephone, because telephone is not a source of what? Charge. Is that clear? So these are the things that can replace cell here to supply charges. It can be what? Accumulator or what? Generator. Is that clear? Or what? Dam. Or what? Dam. I told you that dams can also supply electricity. Is that clear? Like I told you, the major source of our electricity in Nigeria is Kainji Dam. There's also Shiroro Dam. You understand? Gas plants can also supply what? Electric charges that can flow, forming electricity. Is that clear? So an electric circuit is formed when one or more electrical what? Components are connected across the terminals of a what? Cell. In order for the charges that are generated by the cell or accumulator or generator can be done what? Transported. Is that clear? So now we draw the diagram of an what? Electric circuit, and I told us that this is the basic what? Diagram with the what? Symbols representing the basic electrical what? Components. You understand? But in subsequent classes we are going to be drawing elaborate circuit diagrams. We are going to be drawing what? Elaborate circuit diagrams. And when we are drawing these elaborate circuit diagrams, we are going to be using the electrical symbols. So you're supposed to know what these electrical symbols represent. Whenever you see something like this, it represents a what? Cell. When you see something like this, it represents a what? Switch. And that is what we have here, is it not? Another word for switch is what? Key. Is that clear? This is cell. Is it not cell? If this cell is more than 1 or 2, we call it what? Call it what? So cell and battery are the same thing, except as battery is more than 1 cell. Is that clear? Then when you see this, you call it what? Ammeter. A circle with A inside it, ammeter. Ammeter is used in measuring what? Current. Is that not what we learned before? Now we have what? Voltmeter. When you have a circle with V inside, it's known as what? Voltmeter. Voltmeter is an instrument used in measuring what? Potential difference. Used in measuring what? Potential difference of voltage. This is the lamp, or you call it the bulb. Is it not clear? This is what? Battery. Double cell. This is what? Capacitor. Who can tell me the difference between this capacitor diagram and cell? The two standing lines are what? Equal. The two horizontal vertical lines are what? Equal. You understand? But here one is longer, indicating the positive and the negative what? Terminal. Is that clear? This is a what? Switch. This is what? Fixed resistor. This is what? Earth. This is what? Transformer. This is what? Coil. This is what? Cell. This is what? Variable what? Capacitor. Is that clear? So in the subsequent diagram that we'll be making of an electric circuit, we are going to be using this instrument. So I want you to be able to identify this instrument whenever you see them. I want you to do what? Be able to identify these instruments whenever you do what? See them. And these instruments are known as what? Electrical what? Components. They are known as what? Electrical what? And whenever electrical components are connected using wire across the terminals of a battery, it is known as electrical what? Circuit. It is known as what? When you go to all these people repairing TV, you'll be hearing about circuit, is it not? So after today's class, when somebody says circuit, you know what a circuit is, isn't it? Thank you. Yes, welcome. Today we are going to be learning about an electrical component known as resistor. Electrical component known as what? Resistor. What is the work of a resistor in an electric what? Circuit? What is the work of a resistor in an electric what? Circuit? I already told us what an electric circuit is, isn't it? Connection of electrical components using wire across the terminals of a cell, isn't it? So if one of those components is a resistor, what is a resistor? What will be the work of the resistor? A resistor is any electrical material or conductor which forms resistance. Which forms what? Resistance to the free flow of current in the circuit. You understand? Current is flowing like this. All of a sudden something is there preventing the current from flowing easily. So that thing that is there preventing the current from flowing easily is known as what? A resistor. It's known as a what? Resistor. Is that clear? That component that prevents the free flow of electric current in an electric circuit is known as a what? Resistor. Is that clear? And this resistance is measured in what? Ohms. You understand? The ability of a resistor to resist the free flow of current is measured in what? Ohms. It's measured in what? Ohms. And resistors are made of what? Wire. You understand? Carbon or what? Graphite. That is wound round and what? Insulator. One round and a what? Insulator. You understand? That's how you make a resistor. Is that clear? So now you look at the factors that affect the resistance of a wire. What can make the resistance of a wire to be so big or to be so small? What are those factors? JAMB will ask you, which of the following is not a factor affecting the resistance of a wire? And the options we have here is what? Length of a what? Wire. It can be a factor that can affect the what? Resistance of a wire. Cross-sectional area of the insulator plate, temperature of the resistor, or what? The nature of the material that the insulator is made up of. Is that clear? Those are the factors that can affect the what? Resistance of a wire. One is what? Length of the wire, cross-sectional area of the resistor, nature of the material that the resistor is made of, and what? Temperature. Those are the factors that affect the resistance of a wire. Now we look at the determination of the what? Effective resistance of two or more resistors connected in a circuit. Every big circuit that will do a very great amount of work is normally made up of two or more numbers of what? Resistor. It's not only one resistor. So how do you calculate the total resistance or the effective resistance in the circuit? Is that clear? So if you look at the connection here, who can tell me the difference between how this resistor 1, resistor 2, and resistor 3? Who can tell me the difference between the connection here and the connection here? This first connection is not what we know as what? Series connection. Whereas the second one is what we know as what? Parallel connection. Can you see this one? It's moving from one resistor to the other. You understand? Through the wire, back to the terminal. But this one is what? This one diverges. You understand? It's having one resistor on top of the other. You understand? Whenever you have a structure like this, we call it what? Parallel what? Connection. Because they are in parallel lines. Can you see the resistors? They are in parallel. But this one that is meeting one after the other, the terminal of this one meeting with the other one is known as what? Series connection. Is that clear? So whenever you want to find the total resistance for a series connection, you simply do what? Add up the individual resistance. Is that clear? You just add them up. Simple mathematics. Is that clear? But whenever you want to calculate the effective resistance for parallel connection, you have to do the reciprocal of the effective resistance is equal to what? The reciprocals of the different individual what? Resistance. Is that clear? So you make this REF the subject. You understand? And solve down for you to get the effective resistance here. But here is very, very simple. You just add up. So if this is 3 ohms, and this is 2 ohms, and this is 1 ohms, what will be the total resistance, effective resistance? It will be what? 3 plus 2 plus 1, which is what? 6 ohms. You understand? But if this one is 3, this one is 2, this one is 1, can it be 6 again? It will not. You have to get the reciprocal and solve down the mathematics. And that's what we are going to do in the next class. You understand? We are going to look at how to solve these problems. Is that clear? Yes, welcome. Today we are going to be learning about the resistance calculations. Normally in a circuit, we have more than one resistor. We don't have only one. We normally have in circuits that do functions, we have more than one resistor. So if you have resistors that are connected, either in series or in parallel, it is always a question from bodies like JAMB and WAEC that require that you get the effective resistance. Effective resistance simply means the total resistance in a circuit like this. Look at this circuit. This circuit has how many resistors? 1, 2, 3, 4, 5, 6, 7. So what is the effective resistance of this circuit? So when you are asked the effective resistance, it implies the calculation or the manipulation of all these resistors, all the resistance of these resistors, to give us one the resultant resistance. So we are going to learn how to do this calculation. And like we learned in the previous lesson, resistors can be connected in series or in parallel. So connection can either be in series or in parallel. So when you have such resistance connected in either in series or parallel, you're supposed to do the calculation to find out the effective resistance. So number one example that we are having here is determine the effective resistance of the resistors in the circuit below. This is the circuit. You can see that the resistance of this resistor is 3 ohms connected to this one 3 ohms, to another one 2 ohms, to another one 2 ohms, to another one 2 ohms, 3 ohms and 4 ohms. So how do we do this calculation? If you look at this circuit now, you see that if this circuit is redrawn, you can see that this 3 ohm resistor is in series with this 2 ohm resistor, and this is what we try to have here. First of all, we have to, in the solution, we say first we redraw the circuit. We have to redraw the circuit so that we have the right picture. If you look at this 3 ohm resistor and this 2 ohm resistor, you see that they are in series, and that's why here now I connected them in series. This 3 ohm resistor is this one, but this one and this one, I now put them in the normal way that they should be. So you now have 3 ohm resistor here and 2 ohm resistor. Now connected, here we have 2 ohm resistor. Then if you look at this 4 ohm resistor and 3 ohm and this one, you see that all of them are also in series. So you have 4 ohm resistor, 3 ohm resistor, and 2 ohms resistor. So you see that this circuit is the same thing as this circuit, only that it is drawn in such a way that the effective resistance calculation can be done easily. So if you're able to redraw this circuit to be this, then the calculation becomes very simple. This is in series with this, so you can simply add up 3 ohm plus 2 ohm is what? 5 ohms. These three resistors are also in series, so you have 4 ohm plus 3 ohm plus 2 ohms. You have what? 9 ohms. So you now we've now reduced this resistor, this circuit to this. This plus this 5 ohm, this plus this 9 ohms. So we still have the 3 and you still have the 2 ohm resistor. So now you have 2 resistors in parallel, whereas these other ones are in series. So what do? You find the effective resistance of these 2 different resistors. And to find the effective resistance of 2 resistors that are in parallel, you say 1 over R effective equal to 1 over the resistance of one of them, which is 5, plus 1 over the resistance of the other one, which is 9. So finding the LCM of 9 and 5 is 45. So 45 divided by 5, you have 9 times 1, 9. 45 divided by 5, you have by 9, you have 5 times 1, 5. So if you add 9 plus 5, you have 14 all over 45. So if you take the reciprocal, you now have 45 all over 14. So that is the effective resistance of these 2. So if you have the effective resistance of these 2 to be 45 over 14, then you can add it in series with this other remaining 2. So you now have 3 ohm resistor plus this, which is 45 over 14, plus this, which is 2. So you can now simply do the mathematics. You have 3 plus 2, 5, then 5 plus 45 over 14. So I'll allow you to press the calculator so that we can get what 45 over 14 is. Once you get it, add it up. That is the effective resistance of this whole circuit. So you look at the procedure that I've taken. First of all, you have to redraw the circuit, this circuit to give you this. Pick out the ones that are in series easily. 3 plus 2, 5. 4 plus 3 plus 2, 9. Add this one up using the formula for calculating the resistance in parallel, which is 1 over effective resistance equal to 1 over the individual resistors, which are 5 and what 9, to give us 14 over 45. Then take the reciprocal to get the effective resistance to be 45 over 14. So you now add up this 45 over 14 for this plus 3 ohms plus 2 ohms to give us the final effective resistance. So I would like somebody to give me the answer while we close for the day and start again later. Yes, hello, welcome. Today we are going to be looking at the concepts of EMF, electromotive force, EMF, potential difference, PD, efficiency of a cell, and lost volts. So we are looking at 4 concepts in electricity today. Number 1 is electromotive force, EMF. Number 2 is potential difference. Number 3 is efficiency of the cell, and number 4 is lost volt. What is electromotive force, EMF? I told us in the previous class that electric current flows whenever there is supply of charges from a cell. Normally we call a cell battery. Without a battery, you cannot see what is supplying the charges. And when these charges that are supplied flow through the circuit, we have what we call electric current. For current to flow, there has to be a cell. There has to be a battery that supplies the charges. So the electromotive force, EMF of the cell supplying the charges. The electromotive force of a cell is the total energy generated per coulomb. It is the potential difference across the terminals of the cell in an open circuit, and it is measured in volts. So for the battery to supply the charges that will move as a current around the circuit, there has to be a cell. And what is the force in the cell that enables the charges to move? That force is known as electromotive force. So when you have a battery or a cell, the force that enables it to let the current or the electric charge to flow in the circuit is known as the word EMF. So this electromotive force is actually the energy generated per coulomb that enables charges to flow through a circuit, and it is measured in volts. Now we look at the concept of potential difference, PD. If the cell is not connected to other electrical instruments or electrical components, the potential difference across the circuit will just be the EMF of the cell. But once the circuit is connected with other things like resistors, capacitors, and other things, then we talk about potential difference. So potential difference, PD, is the work done in moving an electric charge from one point to another in a circuit. So for a circuit like this that has a resistor, for charges to move from one point of these are the terminals of the cell, for charges to move from here to here, there has to be what we call potential difference, which is the force that enables the charges to move. But for this one, this is another circuit. There is no resistor. It's just the cell itself. So, for charges to move, there has to be a force, and that force is known as EMF. But if the circuit is connected with resistor and other electrical components, the force going is known as potential difference or terminal PD. So you can say that the electromotive force and potential difference are very similar. Just that this is done for an open circuit. Electromotive force is for an open circuit. That is a circuit that is not connected to any other electrical component. Whereas potential difference is the same energy, but this time connected to other electrical components like resistor. So this is also measured in volts. Potential difference is also measured in volts. And it is the energy or the work done in moving an electrical charge. So mathematically it can be represented as PD to be equal to energy obtained or energy over charge. Now we look at efficiency of a cell. How can you make your cell to be more efficient in order to supply enough force or energy that will transport the charges to generate the current? How can you do that? Number one, cells are made efficient if the internal resistance is low. You must make sure that the internal resistance inside the cell, is very low. Once it's low, it can enable much force that will push the charges round the circuit to enable an easy flow of current. Number two is that the electrodes or the plates of the cell have to have large surface area, and they have to be placed close to one another. Like now you can see the electrodes, the two of them, they have to have what we call large surface area, and they need to be placed closer to one another. So when you have a battery or a cell that has the plates have large surface area and they are placed closely to one another, they are going to have what we call higher efficiency. Now we look at a concept known as lost volt. What is lost volt? If you look at these two circuits, you see that this is a cell and it's not connected to any other, it's not connected to a resistor. This is a voltmeter measuring the EMF of this cell, which is the force that enables charges to move, the potential difference across the terminals of the cell. So this voltmeter is just measuring the voltage of this cell. Nothing else is connected. But if you look at this other circuit, the cell is connected to a resistor. So the voltmeter is measuring both the EMF, the difference between the EMF of the cell and the voltage that has been taken off by the resistor. So you can imagine the force here will be bigger than this because the resistor have already taken some force out from this because of the presence of the resistor here. But this one does not have any resistor. So what is the lost voltage or the lost volt? The lost volt is simply the voltage that is measured in this one that does not have resistor, represented as E, or you can call it the EMF of the cell, minus the voltage that is measured when a resistor is connected, represented as the terminal PD, V. So the difference between the voltage here and that measured here, the one measured here and the one measured here, is known as what? Lost volts. So when you are asked to explain the concept of lost volts, you should know that it is simply the voltage difference in the circuit that is made up of only the cell and the one that has a resistor connected to it. So the difference in the voltages that are measured gives you the lost volts of the cell. That is where we are going to stop for today. We've been able to explain three concepts. Electromotive force, like I told you, is the energy that is generated that enables charges to flow through the circuit, causing current. So that force, that energy is known as electromotive force, and that energy is coming from the cell. But when the cell is connected to other things, other electrical components like resistor, we talk about the potential difference between 2 points. You can see that is potential difference. So potential difference and electromotive force, both of them are measured in volts. It's just that this one measures for the cell in an open circuit, whereas this one measures across the whole circuit. Efficiency of a cell, like I told you, what supplies the charges that move through the circuit that causes electric current is the cell. For the cell to be very efficient, it has to have low internal resistance, and the surface area of the plates or the electrode has to be very large, and the electrodes or the plates have to be kept closer to one another. And I told us that lost voltage or lost volts is simply the difference in the voltages that is measured when the cell is not connected to any other appliance or any other electrical component, and the one when the cell is connected to a resistor. So if you take the voltage here, E, which is the electromotive force, minus the voltage across the circuit when a resistor is connected, V, the difference between these two, this one minus this one, gives you the lost volts of the cell. Thank you. Yes, welcome. Today we are going to be looking at Ohm's Law. Who is playing music? Please off it. We are going to be looking at what? Ohm's Law. Ohm's Law is a very popular law in electricity. Is that clear? So we are going to be looking at the statement of Ohm's Law. Ohm's Law states that current passing through a wire. It states that what? The current passing through a wire. Let's say we have a wire that is connected to a what? Cell. Connected to a what? Cell. A wire is always, for current to move, there has to be a cell, isn't it? So, if this is the positive terminal of the cell and this is the negative terminal, you understand? Ohm's Law is telling you that if this is a wire, that the current that is passing through this wire is directly proportional to the what? Potential difference between the ends of the what? Wire. Between the ends of the what? Wire. Let's say the potential difference between here and here. You understand? If the potential difference between here and here is very large, more current will do what? Pass. More current will do what? Flow. If the potential difference between the positive terminal and the negative side is low, lesser current will do what? Flow. So, the more the potential difference, the more the what? Current. Is that clear? That is the statement of what? Ohm's Law. It says that the current passing through a wire is directly proportional to the potential what? Difference between the ends of the wire. Provided that the temperature of the wire remains what? Constant. The temperature of this wire must be equal to what? Constant. It must remain what? Constant. You understand? So the more the potential difference being supplied by the cell, the more current will flow. And like I told you that potential difference or EMF is the force or the energy that enables charges to flow in a circuit, is it not? So this law is simply telling us that the more the potential difference, PD, which is measured in what? Volts. The more the PD, the higher the potential difference, the higher the what? The higher the what? Current. Is that clear? And mathematically you can represent it as saying potential difference V is directly proportional to what? Current. The higher the potential difference, the higher the what? Current. This is how you represent direct proportion in mathematics. Is that clear? Now when V, potential difference is measured in what? Volts, is it not? And is presented by V. Is directly proportional to what? Current, I. Now, if you want to replace this direct proportional variability with equal to sign, you have to introduce a what? Constant. You have to introduce a what? Constant. K. So that you can now say that potential difference V is equal to what? Ki, constant I, which is current. Is that clear? Now, they are trying to tell us that the constant K is a measure of the what? Resistance. It's a measure of the what? Resistance. So you can replace this K with what? R. So that you can have V equal to what? IR. This is a very important equation of electricity. This is a very important what? Equation of electricity. And it is known as the equation of what? Ohm's Law. It is known as the equation of what? Ohm's Law. V equal to what? IR. So in subsequent classes, we are going to be doing calculation using what? V equal to what? IR. Did you see the way we arrived at V equal to IR? Can you see it? So it's very, very important. We are going to be using this equation. And this equation stems from the fact that the current passing through a wire is directly proportional to the what? Potential what? Difference between the ends. Provided that the temperature remains what? Constant. How can you verify Ohm's Law? Verification of Ohm's Law. How can you verify Ohm's Law? You can verify it using what? Voltmeter, ammeter, what? Method. So when you have the voltage, you understand? And you have the ammeter reading. The ammeter measures the what? Current. whereas the voltmeter measures the what? Potential difference. You understand? And it's telling us that as the voltage is increasing, the current is what? Increasing. As the voltage is increasing, the current is what? Increasing. As the voltage is increasing, the current is what? Increasing. So you're going to have a straight line graph, isn't it? When you plot the slope, you get what? The slope will give us the what? Resistance. The slope will give us the what? Resistance. So if you plot this, you're going to verify Ohm's law. Now, what are the limitations of Ohm's law? What are the limitations? You see that in the statement, it says that temperature must be what? Temperature must be what? Constant. So there has to be constant wire temperature. Is that clear? The wire that you're taking for Ohm's law, the temperature must be what? Constant. There should be no tension on the wire. There should be no what? Tension on the wire. You don't need to apply load on this wire. Eh? You just have to keep it the way it is. And the wire must have uniform cross-sectional area. Is that clear? You cannot have a wire like this. And some places bigger and some places thinner. You understand? The wire has to be what? Uniform what? Cross-sectional area. So once you have all this, then you can have the wire to obey Ohm's law. Is that clear? What is Ohm's state? Who can state Ohm's law for me? Ohm's law states that what?
The electrical current passing through the metallic conductor at a constant temperature directly proportional to the potential difference.
Perfect. That is the statement of Ohm's law. The electrical current passing through a wire is directly proportional to the what? Potential difference between each what? Ends, provided that the temperature remains what? Constant. And the Ohm's law equation is what? V equal to what? IR. V equal to what? IR. And you can verify Ohm's law by using the what? Voltmeter ammeter what? Method. And for Ohm's law to be obeyed, there has to be constant wire temperature. There should be no tension on the wire. And there should be uniform cross-sectional area of the what? Wire. And also the wire must be made of the same material. The wire must be made of the same what? The wire material must be the what? The same. You cannot use a wire that part of it is copper and part of it is zinc or something. You understand? There has to be. Exactly.
Oh my God, that's why you do like that.
Hello, welcome. Today we are going to be learning how to measure resistance. Want to learn how to measure the resistance of a resistor. And what is a resistor? A resistor, like I told us in the previous class, is any electrical material that prevents the free flow of electricity. When you have an electric circuit, the work of the resistor, or the definition of a resistor, is that electrical component or electrical material in the electric circuit that prevents the easy flow, the free flow of electricity. So how do we measure the ability of a resistor to prevent the free flow of electricity, which is resistance? How do we measure the resistance of a resistor? How can we measure the ability of a given resistor to prevent the easy flow of electricity? There are three ways to do that. Number one is that we can use the voltmeter ammeter method. Number one is that we can use the voltmeter ammeter method. Number two is that we can use the Winston bridge. We can use a setup or an apparatus known as Winston bridge. And number three, we can use another apparatus known as meter bridge. So three ways of measuring the resistance of a resistor are: number one, voltmeter ammeter method; number two, using a Winston bridge; number three, using a meter bridge. So I'm going to explain all these different ways of measuring resistance. So number one is that we can use voltmeter ammeter method, and this is the setup. You have an electric circuit. This is the voltmeter measuring the voltage across the terminals, and this is the ammeter measuring the current. So if you have a graph where you plot the values that are gotten from the ammeter reading and the voltmeter reading as you vary the variable resistor. You're going to have something like this. This is the volt. If you have V1, you're going to have ammeter reading of I1. So when you have V1, you take it across. When you have I1, you take this reading. When you have V2, you take it to where you have I2, you take this. When you have V3, you take it to where you have I3. You understand? So you measure the corresponding values from the voltmeter and the ammeter. Then when you plot a straight line graph, which is what you're going to get, the slope, which is V all over I, is equal to the what? Resistance. And as you know that, we said that Ohms Law states that V is equal to IR. So if you make R the subject of the formula, you have V all over I, which is also the slope that you will get from plotting the corresponding values of V and I. So that slope is the resistance. So that is one way of measuring the resistance of a resistor. Number two is by having a setup like this. This setup is known as a Winston bridge. This is done by comparing. When you have R unknown, the resistance that you don't know, R, but you know the resistance of R1, R2, and R3. How do you get to know the unknown resistance? So how do you do it? You have to adjust by closing the switches K2 and K1 until there is no deflection in the galvanometer. This is the galvanometer measuring the current. So once there is no deflection, then you balance this equation in this way. The unknown resistance R all over the opposite resistance R3 is equal to R1 all over the opposite resistance R2. So when you make such balance, you make R the subject of the formula, it will give you R1, R3 all over R2. Then you solve the calculation, it will give us the resistance of the unknown resistor. So that's number two way of measuring by comparing the resistance of the ones you know with the one that you don't know in order to get the value of the unknown. Now, using a meter bridge, the meter bridge is simply the practical type of Winston bridge used by comparing resistance of two resistors, R1 and R2, in relation to lengths, L1, L2. So this Winston bridge and the meter bridge, they are very similar, only that you do comparison not just for resistance but also for length. So whenever you have a setup like this, which is a meter bridge, you also close the switch until you have no deflection in the galvanometer. That's when we have a balance point. Whenever you have a balance point, arrange this equation in this way. R1 all over R2 equal to L1 all over L2. L1 all over L2. R1 over L2 equal to L1 all over L2. Make R1 the one you're looking for the subject of the formula. You will now have to solve the calculation of R2 L1 all over L2. Once you find this, this is the one you're looking for. So you also use comparison to find this, just like the way you use here. Unlike using voltmeter ammeter method, where you use plotting of graph and picking readings of the voltmeter and the ammeter. So these are the ways you can use in measuring the resistance of a resistor. Three ways, like I told us. If you want to measure the ability of a resistor to prevent the free flow of current in an electric circuit, there are three ways of doing that. Number one, using the voltmeter ammeter method. Number two, using the Winston bridge method. And number three, using the meter bridge method. So JAMB is going to ask you which of the following is not a way of, or is not a method of measuring resistance of a resistor. So whenever you see these as part of the options, know that there are ways of measuring the resistance of a resistor. Both meter method, Winston bridge method, and meter bridge method. So in subsequent classes, we are going to use these equations that we prepared. The equation for Winston bridge, the equation for meter bridge, to solve calculations. So take note of the balancing of this equation. R for Winston bridge, R all over the opposite. This all over the opposite. Whereas for meter bridge, R1 over R2 all over L1 over L2. Thank you. Yes, welcome. Today we are going to be learning about potentiometer. We are going to be learning about what? Potentiometer. Today we are going to be learning about what? Potentiometer. What is a potentiometer? A potentiometer is an instrument used in measuring the EMF of a cell. Used in measuring the what? EMF of a cell. Electromotive force of a cell. And I taught us what EMF is it not? I said it's the total energy generated that enables charges to flow across a circuit or to flow from a battery or a cell. You understand? Across a circuit, generating current. Is it not? The EMF of a cell is simply the power of the cell. If you have a battery that works with a torchlight, you understand? If you want your torchlight to glow very well, you need to put a battery that has very high watt EMF. The cell has to have high watt EMF. EMF is the energy that will enable the bulb to what? Glow, or that will enable the current to what? Flow. So how do you measure this EMF of a battery or a cell? Not your cell or your battery. If you want to measure the power, how do you measure? You measure using an instrument known as what? Potentiometer. Using an instrument known as what? Using an instrument known as what? Potentiometer. You understand? So this potentiometer is an instrument for measuring the EMF of a cell. You can also use it to compare the EMF of two cells. You understand? You don't just use it to measure the EMF. You can also use it to do what? Compare the EMF of what? Two cells. So how do you do that? It consists of a meter length wire. It consists of a what? Meter length wire. The length of the wire is 1 watt meter. 1 watt meter. Mounted on a board. Mounted on a what? Board. Alongside a what? Meter row. This is a meter row. Can you see this? This is the wire mounted on the meter row. If you use, whenever you want to use it to measure, you understand? A steady current from a cell connected across the wire flows. This is the cell, is it not? So a steady current from a cell connected flows. You understand? The length from A is measured. Can you see A? Can you see B? So you measure this length from A. You understand? So when you put your galvanometer here, you measure. You understand? You put it in another place. You do what? Measure. You get the length. So whenever you put your galvanometer and it's indicating no current flow, you know that you've arrived at the what? Balance point. You know that you've arrived at the what? Balance point. So at the balance point, how do you do the calculation to find the unknown EMF, the E2 that you're looking for? How do you find it? You simply say what? E1 over what? E2 to be equal to what? L1 all over what? L2. You understand? Then make E2 the subject of the formula. E2 will simply be equal to what? E1 L2 all over what? L1. So simplifying it, so simply say that at balance point of the potentiometer, E1 over E2 is equal to what? L1 over what? L2. Similar to the calculation we did for meter bridge, is it not? So whenever you want to measure the EMF of a cell, the EMF, the electromotive force of a cell, you use an instrument known as what? Potentiometer. You use it to measure EMF. Exactly. You also use it to compare the EMF of two cells. Potentiometer, you understand? Take note of the what? The equation. E1, which is the electromotive force of the cell, 1 over that of cell, so equal to the length measured from the point when there is a balance to the length L2. Is that clear? Thank you. Yeah, today we are going to be looking at electricity calculations. We are going to be looking at what? Electricity calculations. In JAMB, in your JAMB and in your WAEC, you are supposed to do calculations on resistance, EMF, voltage. You understand? All those calculations you're supposed to do it. So we're going to be taking some examples, 1 or 2 or 3 examples, to get you in tune to what you are required to do. So you can have such question in JAMB. A cell having an EMF of 1.5 volts and an internal resistance of 2.0 ohms is connected in series with an ammeter of resistance 0.3 ohm and a resistor of resistance 8 ohms. Determine the ammeter reading. When you are asked determine the ammeter reading, what are you asked? To measure the what? Current, the ammeter reading. All of us know that ammeter measures current. So when they tell you to determine the ammeter reading, they are simply telling you to calculate what? Current. Then number 2, determine the potential difference across the terminals of the word cell. So when you're given a statement like this or a problem like this, first of all, try and understand the question. First of all, try and do what? Understand the question. So relate this question with the diagram that will be given to you. They are going to also give you this diagram. They are going to also do what? They are going to also give you the diagram. So try and understand the question you are asking in relation to the what diagram. So let's take the 2 of them together. A cell having EMF. This is the cell, is it not? The cell has EMF of what? 1.5. Can you see that? And internal resistance of what? 2 ohms, 2.0. There is a mistake here. Right? So I'm supposed to put 2.0 ohms. Can you see that? So this EMF of 1.5 volts and resistance of 2.0 ohms, they are the properties of this cell. They are the properties of what? This cell alone. You understand? So whenever you are representing the internal resistance of a cell, you use lowercase r. You use lowercase what? But when you are representing the normal resistance, you use what? Higher uppercase what? R. But here you see r. This r, and this r, all of them means resistance, is it not? But this small one means internal resistance of a what? Cell. But this one is the normal resistor resistance. Is that clear? So here, a cell having EMF of 1.5 volts and internal resistance of what? 2 ohms is connected in series. Is connected in what? Is connected in what? Series. To an ammeter of resistance what? 0.3 ohm. Can you see that ammeter? In series to an ammeter of 0.3 ohms and a resistor of resistance what? 8 ohms. Can you see? All of them are in series. All of them are in what? Series. Now they are asking you now, determine the ammeter reading. That is, calculate the current that is passing through this ammeter. Can you see the ammeter? Yes. Determine the ammeter reading. So how do you go about this? You use the loss volts relation. Can you remember the loss volts relation? It's in your notes. Good. Difference between the potential difference when it is only the what? Cell and when resistors are what? Connected. That's loss volts relation, is it not? So when you now put this make EMF of the cell the subject, you are going to get that E is equal to what? IR, which is what? The voltage of the whole circuit plus what? I small r, which is the what? The voltage on the what? Cell alone. Is it not? So we have E equal to what? I in bracket. This thing, if you are writing it in full, what you should have had is what? E is equal to what? I big R plus what? I what? Small r. Is it not? You took I out of the bracket, that's why you saw it. And we know that this thing now can be equal to E, equal to I big R is what? V. Is it not? Then this other one is what? This other one is EMF. This other one is what? EMF. You understand? Can you understand this? So that this one now is equal to E minus what? V. Equal to this one. Is it not? Which is the loss volts equation. Open your loss volts equation note. Let me see it. What did we say is loss volts? Loss volts. That is it. Lost volts. That is it. Who has it? Let me see.
Like this time now. I think
That's the question.
next week was they just something like that. So we get time balance. So we do the day
You have it there. Good. That's the question.
Get my point.
It has. You didn't copy it, please. This is the last words equation I gave you the last time we had a class. Lost volts is equal to what? E minus what? V. Is it not? E minus V is equal to lost volts. Is it not? So check the last equation that we did. You see this equation. So in essence, it comes to this. You understand? So now to get the ammeter reading, you say that you make what? Current the subject of the formula. You make what? Current the subject of the formula. So when you make current the subject of the formula here, you have what? I equal to what? E all over what? Big R plus what? Small r. Is that clear? So, for the effective resistance, you need to calculate the effective resistance, which is the resistance here plus the resistance what? Here. And they are connected in what? Series. So how do you calculate it? You simply add them together. So you have 8 plus what? 3. 8 plus 1, 0.3, giving you what? 8.3. That is the effective resistance. So now current now is equal to what? E. What is E? 1.5. All over what? The effective resistance R, which is what? 8.3 plus the internal resistance, which is what? 2.0. You understand? So that you have 1.5 all over 10.3, giving us what? 0.15 E. Is that clear? So that is the ammeter reading. So we've solved the number 1, is it not? Now to solve number 2, which is what? Potential difference across the terminals of the what? Cell. What is the potential difference? Total potential difference in the what? External circuit. You know that this cell is supplying the external circuit. You understand? So the potential difference across the terminal of this cell is the total what? Potential difference in the external circuit, which is simply IR. You understand? Which is simply what? IR. That is what? Current times what? Resistance. We know that potential difference V is equal to what? IR. Is it not Ohms Law? So potential difference is equal to I all over what? Effective resistance, which is R1 plus what? R2, which is equal to 0.15, which is the value of the current we got, times what? 8 plus what? 0.3, giving us what? 1.2 volts. Is that clear? So check this out. This is how you make the calculation. This is how you do what? This is how you do the calculation. You are supposed to study the equations that I've given you already. All the equations that I've given you already. They are very, very important. When you get them down, you understand this more. Read the question very well. Look at the diagram. Relate the equation with the diagram. Then check the equations from the ones I've given you. The best one, like I told you, this one, the best equation to use in solving for the ammeter reading is what? Lost volts equation is the what? This is equal to what? Lost volts. E minus V equal to this. You understand? So if you write it in another way, you have this. Make I the subject of the formula. Calculate the what? Effective resistance. Solve for I. Then use the value of I, which is current that you've got, and multiply it by the effective resistance of the external circuit. To get the what? Voltage, which is what you are asked. Is that clear? Is that clear? Yes, welcome. Today we are going to be learning about capacitors. We are going to be learning about what? Capacitors. Capacitors are electrical materials that are used to store charges. When you go to some houses, they have what we call inverter in their house. When the NEPA takes light, there will still be light in their house. Why? Because they have inverters. Those inverters that they have are made up of capacitors. And why are they still having light? Because the capacitors that are inside the inverter, they are able to store the charges. The NEPA light, when the NEPA light is still on, they will be storing the charge. So that when NEPA goes out, the charges that are already stored in the capacitor will be used to lighten up the house, and you can use it to do other things. So you see that capacitors are very, very important in our everyday life. So today we're going to be treating capacitors in electricity. So what are capacitors, or what is a capacitor? A capacitor is an electrical material used for storing electric charges. So a capacitor is an electrical material used for storing electrical charges. Our inverter is made up of capacitors, like I told us, the inverters that we have in our houses and in our offices, that even when there is no NEPA light, no PLC, no electricity, we are still able to have light or have electricity. So those inverters are made up of capacitors. And basically, what are the components of a capacitor? A capacitor consists of two metal plates. A capacitor consists of a plate like this and another plate. Two metal plates separated by an insulator. And this insulator is called a dielectric. And it can also be separated by oil or air. So depending on the insulator that you're using, you can have one that is separated by oil or air. And a capacitor is represented using this symbol. This is the symbol of a capacitor. When you're drawing an electric circuit, you make sure that you represent a capacitor with this symbol. If you are representing a cell, it will be like this. This is the positive terminal and the negative. But for a capacitor, the two vertical lines are equal. Now we have different types of capacitors. We have what we call the fixed capacitor. We have the variable capacitor. We have the leading jar capacitor and the electrolytic capacitor. So we have four types of capacitors: fixed, variable, leading jar, and electrolytic capacitor. Now we talk about the capacitance of a capacitor. The ability of a capacitor to store charges. So a capacitor that has very high capacitance means that it will store more charge, so that when the NEPA light or when the electricity goes out, it can supply much light. But if this capacitor has very small capacitance, the power is lesser. So what is the capacitance of a capacitor? The capacitance of a capacitor is simply the amount of charges received when the potential difference between the two parallel plates is equal to 1 volt. That is the for unit capacitance. So, and it can be represented by saying C equal to charge all over volts. So capacitance of a capacitor is simply equal to the amount of charge stored all over the potential voltage measured in volts. And this capacitance of a capacitor can be measured in farad. Farad, that's the SI unit, or the basic unit for measuring capacitance, farad. And it has smaller units like picofarad, which is 10 to the power minus 12 farad. And you can also have microfarad. This is the most commonly used unit, smaller unit of farad, microfarad, and it's simply equal to 10 to the power minus 6 farad. So in subsequent calculations, we are going to be using this formula. Capacitance is equal to quantity of charge all over voltage, potential difference. So in the next class, we are going to be looking at the factors that affect the capacitance of a capacitor. Yes, welcome again. Today we are going to be looking at the factors affecting the capacitance of a parallel plate capacitor. What are those factors that will affect the power of the capacitor to store charges? I told us that the power of a capacitor to store as much charges as possible is known as its capacitance. The volume of the charge that it can store per potential difference available across these terminals is known as its capacitance. So what are those factors that affect the capacitance? What are those things that make the capacitance to be either too high or too low? What are those things that you take into consideration when you are building a capacitor in order to ensure that the capacitance is high? What are those factors that affect the capacitance of a capacitor? Number one, the effective surface area of the two parallel plates. I told us that a capacitor is an electrical equipment like this. It has two parallel plates, and in between the parallel plates there is a dielectric material. So these parallel plates, they are plates like this. This is a plate, this is another plate, they are placed like this. So the surface area, the surface of each of these plates, if the surface area is high, the capacitance will be high. That's why it has a direct proportionality. Capacitance is directly proportional to the surface, effective surface area. Meaning that the higher the surface area, the higher the capacitance of a capacitor. So C is directly proportional to A. So when you're constructing your capacitor, make sure that the effective surface area of the plates are large enough to make the capacitance to be high. Secondly, the distance between the parallel plates. What's the distance between these plates and these plates? The distance. This distance between the two plates. The capacitance of the capacitor is inversely proportional to the distance. That means the more the distance, the lesser the capacitance. So you have to make sure that the two plates are close to each other. Because if the distance is big, then the capacitance will be small. So make sure that you have this distance to be very small so that the capacitance will be large. So C is inversely proportional to distance D. The third factor affecting the capacitance of the capacitor is the presence of dielectric material. So the nature of the dielectric material inside that separates the two plates matters a lot. So you make sure that you use a dielectric material that will enable the capacitance to be high. So generally, when you combine this and this, you see that C is directly proportional to A, which is the surface effective surface area, but inversely proportional to D. So you have C proportional to A over D. So if you take out this proportionality sign to change it to equal to, you introduce a constant mu, and this constant is simply the permittivity of free space or vacuum, representing what you use as your dielectric material. So in essence, you have the general equation of a capacitor, of the capacitance of a capacitor, considering the factors that affect its magnitude to be equal to this equation, A over D with this constant. So this equation, take note of this equation because we are going to be using it. Where this sign represents the permittivity of free space or vacuum, and the value is 8.84 times 10 to the power 12 farad per meter. Farad per meter. So take note, in subsequent classes we'll be using this equation to solve problems of capacitance. Thank you.
That is not only my name,
Yes, welcome. Today we're going to be looking at some concepts in our lectures on capacitor. We're going to be looking at electric field in the capacitor, work done in a capacitor, relationship between electric field, potential difference, and distance between parallel plates, and finally the energy stored in a capacitor. We're going to be giving us these relations and equations which are very, very needed when you're solving problems in capacitor, like when you're doing WAEC, GC, NECO, or JAMB. These relations are very, very important. And number one is the electric field in the capacitor, which is simply the measure of the charge intensity, the intensity of the charge, the intensity of the charge in the capacitor.
I never
It is simply the force per
verification
unit charge,
after
F
I
over
joined
Q.
my
The electric field
tech
in
day.
capacitor is simply represented as
Maybe around
force over quantity of charge, F over Q. And the work done in a capacitor is simply the work done in moving a positive charge from infinity to a particular point in the capacitor. So that work done in moving a positive charge from infinity to a particular point in a capacitor is known as the work done in a capacitor. And it is represented with the relation, the work done is simply QV. And we all know that work done is equal to force times distance. So if we equate QV, which is the work done in moving a positive charge from infinity to a particular point in the capacitor, if we equate it to the normal relation of work done, which is force times distance, we have that making F the subject of the formula. Force is equal to QV all over D. This is the relationship is very, very important. This equation, you need to take note of it. The force needed to move or the force on a positive charge, or the force needed to move a positive charge from infinity to a particular point is equal to QV all over D. Very, very important relation. You need to know it. Now, when we look at the relationship between electric field E, potential difference V, and distance between parallel plates. Distance between parallel plates. I told us that this is the representation of a capacitor. So if we are looking at the voltage between the terminals, potential difference, the electric field inside, the electric field inside, and the what distance between the plates, the distance between the two plates, these two plates, distance. What is the relationship that relates those things together? The potential difference between these 2 points, the electric field, and the distance between the plates. Since E is equal to F over Q from this one, electric field, we say that is the force intensity of force per charge. And F, as we know from here, is equal to QV over D. Then we can say that E is equal to QV over D, which is the value of force from here, all over Q. So Q cancel Q, will be left with V over D. So in essence, the electric field is simply equal to the potential difference all over the distance. So this electric field between the plates is equal to the potential difference across the terminals of the capacitor all over the distance between the capacitor. Very, very important relation. Electric field equal to potential difference all over distance. Take note of this. We are going to be using it in subsequent calculations. And finally, we look at the energy stored in a capacitor. How do we calculate the energy stored in a capacitor? Energy stored in a capacitor is simply equal to half 1 over 2 CV squared. Very, very important formula. If we don't want to use 1 over 2 CV squared, we can use 1 over 2 QV. 1 over 2 QV. Very, very important. You can use either of these equations to calculate the energy stored in a capacitor, which we are going to be doing in subsequent classes. Thank you. Yes, welcome. Today we're going to be looking at determination of the effective capacitance of a capacitor of capacitors in parallel and in series. You remember when we are doing resistance of resistors, we said that when it's connected in parallel, like this is parallel connection. For resistor, it would have been 1 over R plus 1 over R2, 1 over R1 plus 1 over R2. But for capacitance, it's the reverse. Yes. So for parallel connection, you have effective capacitance to be equal to C1 plus C2, C1 plus C2. But when we have a series connection, this sort of connection is series connection, C1 and C2. We have effective 1 over effective resistance will be equal to 1 over C1 over 1 over C2, making effective capacitance is subject of the formula. You have effective capacitance to be equal to C1 C2 all over C1 plus C2. So capacitance is just the reverse in terms of looking at the calculation for the effective capacitance in series and in parallel connection is a reverse of what we had in resistance of a resistor. So now we're going to do calculation with this. So whenever the capacitance is connected, whenever the capacitors are connected in parallel, you use direct addition. But whenever they are connected in series, you use the reciprocal. You add up the reciprocal as well as the reciprocal of the capacitance. So take note of these relations. Now, the calculation, we are going to try one calculation. Now we have in the equation, example 1. 3 capacitors are connected in what? Series. You can see it's in series. So you're supposed to have something like this. 3 microfarad, 4 microfarad, and 2 microfarad. So they are connected in series. So whenever you have a series connection, how do you solve the calculation? How do you solve the calculation for series connection? So you're going to have that the effective capacitance will be equal to 1 over C1 plus 1 over C2 plus 1 over C3, which is simply equal to 1 over 3 plus 1 over 4 plus 2 plus 1 over 2. So that's how you calculate the effective resistance. But let's look at the equation completely. 3 capacitors of capacitance 3 microfarad, 4 microfarad, and 2 microfarad are connected in series in electric circuit. If a 500 voltage DC source is connected across the capacitor, determine the total energy stored in the circuit. So how do you calculate this? First of all, you need to determine the effective capacitance. So this is what you do. So when you now say 1 over C, effective capacitance will be equal to, you add this up. How can you add this up? You get the LCM of 3, 4, and 2, and that is what? 12. So 12 divided by 3, 12 divided by 3 is what? 4. 4 times 1, 4 plus. 12 divided by 4, 3. 3 times 1, 3 plus. 12 divided by 2, 6. 6 times 1, 6. So you have this 4 plus 3 plus 6, giving us what? 13 all over what? 12. So if 1 over C effective capacitance is equal to 13 over 12, that means that effective capacitance is actually equal to 12 over 13. So that is our effective capacitance, 12 over 13. What is the value of 12 over 13? Press your calculator. 0.923 microfarad. So we have effective capacitance C to be equal to what? 0.99 what? 231 microfarad. So that is the effective capacitance. So now we are supposed to find the value of the what? What are we supposed to find? To determine the total energy stored. And what is the value of the energy stored? Check the equation I gave you before. Energy stored in a capacitor. What is the formula for calculating the energy stored in a capacitor? I told us that is equal to what? Half C, half what? Half CV squared. So it's simply equal to half C. C, what is C? The value of the effective capacitance, 0.9231 microfarad. When you convert it, it will be 10 to the power what? Microfarad is 10 to the power what? Minus 6, converting it to normal farad. So times V square. What is V? 500. 500 squared. So when you solve out this calculation, you're going to get 11.534. 11.534 times 10 to the power minus 2 joules. So press this out in your calculator. That will be your answer. So first of all, in approaching this question, what did we do? we found out the effective capacitance. And how do we do it? Because they are connected in series, we say 1 over effective capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. We'll put them and solve out the effective capacitance, which we arrived at was 0.9231 microfarad. You need to convert this microfarad to farad. That's why we multiplied it by 10 to the power minus 6. So putting it in this formula for energy stored in a capacitor, we solve out to get this. Thank you.
You feel open this one. Shall we open it?
I don't agree. Just show me make
Why
a.
don't you open the two of them? You understand? So that you will get side by side. You don't go there, go the copy and the post for you. You understand? This is the new one I created. The old one is inside my own. This one was just my assignment. And just remove the manual.
Supposed to open with the folders, with the files. All those things. Like this mini challenge now, I need to do one before. This one said, no. Open that mini challenge first. And the first one we have. And this one said do before what? Wait, hold on. Open this one first. This one, I know. I don't do this one before.
I go use this one.
So, just copy. Make I just try. Thank you.
Yes, welcome. Today we're going to be looking at determination of the effective capacitance of a capacitor of capacitors in parallel and in series. You remember when we are doing resistance of resistors, we said that when it's connected in parallel, like this is parallel connection. For resistor, it would have been 1 over R plus 1 over R2, 1 over R1 plus 1 over R2. But for capacitance, it's the reverse. So for parallel connection, you have effective capacitance to be equal to C1 plus C2, C1 plus C2. But when we have a series connection, this sort of connection is series connection, C1 and C2. We have effective 1 over effective resistance will be equal to 1 over C1 over 1 over C2, making effective capacitance the subject of the formula. You have effective capacitance will be equal to C1 C2 all over C1 plus C2. So capacitance is just the reverse in terms of looking at the calculation for the effective capacitance in series and in parallel connection is a reverse of what we had in resistance of a resistor. So now we're going to do calculation with this. So whenever the capacitance is connected, whenever the capacitors are connected in parallel, you use direct addition. But whenever they are connected in series, you use the reciprocal. You add up the reciprocal, as well as the reciprocal of the effective capacitance. So take note of these relations. Now, the calculation, we are going to try one calculation. Now we have in the equation, example 1, 3 capacitors are connected in in what? Series. You can see it's in series. So you're supposed to have something like this. 3 microfarad, 4 microfarad, and 2 microfarad. So they are connected in series. So whenever you have a series connection, how do you solve the calculation? How do you solve the calculation for series connection? So you're going to have that the effective capacitance will be equal to 1 over C1 plus 1 over C2 plus 1 over C3, which is simply equal to 1 over 3 plus 1 over 4 plus 2 plus 1 over 2. So that's how you calculate the effective resistance. But let's look at the question completely. 3 capacitors of capacitance 3 microfarad, 4 microfarad, and 2 microfarad are connected in series in electric circuit. If a 500 voltage DC source is connected across the capacitor, determine the total energy stored in the circuit. So how do you calculate this? First of all, you need to determine the effective capacitance. So this is what you do. So when you now say 1 over C effective capacitance will be equal to, you add this up. How can you add this up? You get the LCM of 3, 4, and 2, and that is what? 12. So 12 divided by 3, 12 divided by 3 is what? 4. 4 times 1, 4 plus. 12 divided by 4, 3. 3 times 1, 3 plus. 12 divided by 2, 6. 6 times 1, 6. So you have this 4 plus 3 plus 6, giving us what? 13 all over what? 12. So if 1 over C effective capacitance is equal to 13 over 12, that means that effective capacitance is actually equal to 12 over 13. So that is our effective capacitance, 12 over 13. What is the value of 12 over 13? Press your calculator. 0.923 microfarad. So we have effective capacitance C to be equal to what? 0.99 what? 231 microfarad. So that is the effective capacitance. So now we are supposed to find the value of the what? What are we supposed to find? To determine the total energy stored. And what is the value of the energy stored? Check the equation I gave you before. Energy stored in a capacitor. What is the formula for calculating the energy stored in a capacitor? I told us that is equal to what? Half C, half what? Half CV squared. So it's simply equal to half C. C, what is C? The value of the effective capacitance, 0.9231 microfarad. When you convert it, it will be 10 to the power what? Microfarad is 10 to the power what? Minus 6, converting it to normal farad. So times V squared. What is V? 500. 500 squared. So when you solve out this calculation, you're going to get 11.534. 11.534 times 10 to the power minus 2 joules. So press this out in your calculator. That will be your answer. So first of all, in approaching this question, what did we do? We found out the effective capacitance. And how do we do it? Because they are connected in series, we say 1 over effective capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. We'll put them and solve out the effective capacitance, which we arrived at was 0.9231 microfarad. You need to convert this microfarad to farad. That's why we multiplied it by 10 to the power minus 6. So putting it in this formula for energy stored in a capacitor, we solve out to get this. Thank you.